Hey guys, so I'm just going to do a quick recording of the practice final. So if you have any little questions, you can just look at this video. And if you have more detailed questions, you can email us or come to the official TA review session, which will be next week. So the first thing for the practice final is to load your R data in. So we just download the R data, and then you do File, Open File, and go to your downloads. And you'll click on that sample final data and hit open and hit yes. And then all of your data will show up in your global environment. So for question 1, it tells us that a university offers 2-degree programs, and we're seeing the difference between likelihood to get admitted between males and females. So to see the difference in likelihood, I'll make a table of that admissions data. And from the table, you can see that 50% of females were admitted, 10 were admitted, and 10 were denied. So 10 divided by 20, that's 50% of females were admitted. For men in engineering, 30 were admitted, 30 were denied. So 50% of males were admitted. So for engineering, it's 50% whether you're male or female. And then you look at English, 10 were admitted, 30 were denied. So 10 divided by 40, 25% of females were admitted. And then for men, 5 divided by 20, 25% of males were admitted. So we see that there is no association between gender and admission decision in either program. Whether you're male or female, you have the same likelihood of getting admitted. Question 2. So it's giving us data from this Anaconda music video views, and we're trying to see if it's symmetric, skewed, or if it looks nearly normal. So for that, we just do a histogram, which is the hist function, and you'll do views, $, the column, and when we run that, and you can hit zoom to zoom in on the plot, and we see that there's outliers to the right, so this is skewed to the right. Question 3. It gave us this home price data set, and it says use the data to predict the listed price for a 2,300 square foot home. So in order to predict an X value, we need to make an equation first, which we do with a linear model, the LM function. And with LM, we always put Y first, and then we put the squiggly, and then we put X. So we're trying to use the square footage to predict the price. So we put home price, the price first, and then our little squiggly sign, and then the square feet. And we do that with LM. And you can call it whatever you want. I just called it model. And when we run that, it ran and it made this thing called model. And then I do summary of the model I just made. And it gives me the coefficients. It gives me the intercepts, and it gives me the slope of square feet. So the next step is to plug in the 2,300, which is our X, times the slope, and then add the intercept to find the price of the home. So we run that, and then you can name it price, and then just type price, and it'll tell you what the price is down here, and it says 417. So that's our answer. In question 4, it is about this same home price data set, but now it's saying, are we seeing if the residual plot means that the assumptions are checked? So a lot of people don't remember how to do this. So in order to make the residual plot, we have to do that same LM function that we just did, home price with the LM with Y in terms of X. So I ran that same model, same line of code we just did in question 3. And then we use the residuals function to find the residuals, which are the differences between the predicted values and the actual values. So I can run this, and it made the residuals, and then I do plot, and I put my x variable, which is square feet, comma residuals. So plot x comma y, and we look at this plot and we see there's a clear fan. It spreads out as x increases. So with homes for bigger square feet, there's a greater residual. We're not as good at predicting the price. So when we look at the answer choices, it says prediction of listing price will be less accurate when the home size is larger because the residual plot shows increasing spread about the line. As it fans out, the residuals get bigger, so we're not as good about predicting those bigger sized homes. Okay, question 5. 20% of homes in Austin have a fireplace. 64% have a driveway, and of houses with driveways, 30% have a fireplace. And it asks what proportion of homes have both a fireplace and a driveway. So this is just knowing your probability formulas, which you will write on your cheat sheet. And this one is P of A and B equals P of A times P of B given A. So we have to look in this question, what did they give us? They gave us of houses with driveways, 30% have a fireplace. So when we look at this, that means probability of fireplaces given driveways is 0.3. Of houses with driveways, that means given driveways, 30% have fireplaces. So that means fireplaces is B, given driveways is A. So I'm going to multiply 0.3 times something. But then we see, okay, it's P of A times P of B given A. So we know driveways was A, so we have to multiply it times the probability of driveways, which is 0.64. So we do 0.3 times 0.64, which gives us 0.192 for our probability. So just know that equation, write it down, and read the question and be careful about what is B and what is A. Now question number 6. So it says, consider an investment opportunity with possible annual returns between 25% and negative 12%. And all of those outcomes are given in our investment file. The standard deviation is a measure of risk of the investment. And so we can't just do SD of this column because each of these investment returns have a different probability. So I can't just do SD of the percent return. I have to mess around with it and do it in a specific way. And this is code that you'll probably also write on your cheat sheet, just to know. So in order to find the expected value, we do the percent returns times the probability. And what that did was just make kind of like a new column with all of the returns times all of the probabilities in a new column. And then I sum up all of those, and the expected return is 4.58%. So in order to find the standard deviation, I do each of these percent returns minus the mean, which was the expected value that we just found, and all of those squared. So those are all of the squared deviations of each return from the mean. Now I times all of those squared deviations times the probability, which are all of these numbers. And then I sum all of those to find the variance. And then we square root the variance to find the standard deviation. This is code that you'll just write down. Remember, this is all of your example, like x's. This is your probabilities. And our answer is 10.009. Question 7. So this question is saying the Shaquille O'Neal's free throw percentage is 52.8% for one free throw. And we're looking at the probability that he makes at least 2 out of 3 free throws. So this is binomial because Shaquille O'Neal either can make the free throw or he can't make the free throw. And the probability is the same on every free throw, 52.8%. And we're assuming that these are independent. Each free throw is independent of another free throw. So we'll use the p-binom function because we know this is binomial. And when we just do binom, it's the probability of making 1 or less, and the total number of trials, which is 3, and the probability of getting each trial a success. So if I just did p-binom of 1, 3, 0.528, this would be the probability of making 1 or less. The probability of making 2 or more is 1 minus that. So that'll give us 0.542. Question number 8. The weight of a randomly selected can of a soft drink is this mean and this standard deviation. And it's saying the weight that should be stamped on the can so that only 2% of cans are underweight is closest to one of these numbers. So this is a normal question because it's continuous, and we're seeing that the weight that 2% of cans are underweight. So that's the bottom 2% of a normal curve. So I'm looking for the bottom 2% of this normal curve. So we use Q norm when we're given a percentage and we're looking for quantity. We're looking for the number. If you're given the number and looking for the percentage, you would use P norm. So we're looking for the bottom 2%. That's why we use Q norm, with a mean of 8.3 at a standard deviation of 0.2. So Q norm, we put percent, comma, mean, comma, standard deviation. For P norm, you'll put the value, comma, mean, comma, standard deviation. So when we run this, we see that it is 7.89. So that will give us the 7.9 answer. Question 9. We're designing a survey about the City of Austin transportation system. Which of the following questions would be the best way to obtain clear data on bicycle use using unbiased wording? So we're looking for 2 things. We're looking for clear data and we're looking for unbiased wording. A lot of people don't like these questions, but this one is actually pretty simple. So we can get rid of 3 right away because it says how often do you ride your bike to work? Often, occasionally, or never. Those are not defined, and people can interpret these different ways, so that's why we will not select C. And A, how many days a week do you ride your bike in a lane intended for automobile traffic? So that is biased towards people. We don't want people to ride their bikes because it says intended for automobile traffic. And B says, how many days a week do you help the environment by not emitting greenhouse gases while riding your bicycle? That's biased toward people who want to ride their bicycles. So that leaves us with D. How many days a week do you use a bicycle to go from home to work? Not biased, and it gives us the specific days a week. Okay, number 10. In 1995, the Gallup poll asked a sample of 620 people whether their support of baseball had been affected by the players' strike. 248 people in the sample said yes. If the Gallup poll had asked 1,500 people rather than 620 people, the margin of error would be. So, this is saying, how does sample size affect margin of error? So look at the margin of error, which I wrote right here. It's our Z star times square root of P times Q divided by N. So if I increase N, make N bigger, I'm dividing by a bigger number, so my margin of error is going to be smaller. So that gives us less because the sample is now larger. Now we're on question 11. So this question is about a platinum card benefit, and the previous, before the loss, we saw that the percent of people that rated the card's benefits as excellent was 0.35. And then we did the survey and we saw that 33% of people in the survey, in the sample, rated the benefits as excellent. So it's asking us for the p-value of the test. So we know 0.35s are null, and our sample one was 0.33. So when we do our p-value without a data set, I'll define my n, which is my sample size. It told us card users. Null was 0.35, which is here. And which is our sample proportion, was 0.33. So I'll define all of these. And then we find our standard deviation, which is square root of p null times 1 minus the p null divided by n. And then I find my p-value using p-norm. And I put my p-hat in, and then I put my p-null, and I put the standard deviation that I calculated. We find that our p-value is 0.134. Question 12. This is about what a confidence interval means, which a lot of people struggle with. So it tells us a random sample of American men is taken in which the weight of each man is recorded. Suppose a 99% confidence interval for the mean weight of an American male is calculated to be this. This means that the number one thing you need to remember about confidence intervals is that they are trying to find the true proportion of the population. Confidence intervals don't tell us anything about an individual sample. They don't tell us anything about an individual person. They tell us about the true mean. So, 99% of adult men are between these weights. No. This is talking about specific people. That's why that's not right. We have constructed an interval using a procedure that will include the true mean 99% of the time. Yes. If the sample were repeated many times, the average weight would be between this. This is about samples. Confidence intervals are not about samples. So this confidence interval means that if I take 100 samples, 99 of those samples will contain the true mean. So for question number 13, suppose that the measurements of a chemical in wastewater from a mill vary over time according to a normal distribution with this and the standard deviation. Measurements on 9 dates are taken and the sample mean is reported. If the sample mean is 0.006 or above, the mill will be required to pay a fine. So the number we care about is 0.006. We put it in here, and we're saying 0.06 or above. So that's 1 minus, and I put in my mean, and because it's sample mean, we can't just put 0.0012 for the standard deviation. We have to put the population standard deviation divided by the square root of the sample size. So that's why I did 0.0012 divided by square root of n. So p-norm, we put our value, comma mean, comma standard deviation, which in this case is standard deviation of the sample, and we did 1 minus because it's 0.06 or above. And we get 0.006 for our probability. A government agency is concerned about deterioration of automobile anti-pollution equipment after cars are sold. The agency took a sample of 19 cars at dealers and a year later took a second sample of 18 cars that had been in service for at least 8 months. The nitrogen oxide readings are given in this file. Carry out the test to see if there is strong evidence that the means are different. So we know we're doing a two-sample t-test because we're trying to see whether the means are different. And it's going to be two-sided because if the means are different, not if one is greater than the other or if one is less than the other. We're just seeing if they're different. So when we look at the Knox file, and there's a column called new and a column called used. And what you need to realize in this question is that the 19 cars are not the same cars as these 18 cars. So this is not paired. It's a two-sample independent t-test. That's why we just do test, comma, used. That's all you have to do for this question. It's not paired, and it's two-sided. And we get that our p-value is 0.13. And the rounding is a little weird for this question, but it's close enough. Number 15. Two laboratory procedures for determining the amylase level in human body fluids are compared. The new method is less expensive than the standard method, but may give different results. Both methods are used on each of 10 subjects. This is our hint that this is a paired test. We had 10 subjects, and both methods were used on each subject. So the results are given in this file, and we're trying to find the confidence interval for these subjects. So we can go look at the amylase file. And another hint that this is paired, that subject 1, we have two values for subject 1. Subject 2, we have two values. This is another hint that this is a paired test. So we're just going to use our t-test function because it gave us the values super easy. And this is a confidence interval. So it's also 90%, which t-test defaults to. So you don't have to add anything into the t-test function. If it were different, you would have to do conf.level equals whatever your confidence level was. Since this was 0.95, we're good. We don't have to put that in there. So we're going to put comma standard and equals true. T-test defaults to paired equals false. So if it is not paired, you don't have to put anything. If it is paired, you have to put paired equals true, or else you're going to get the wrong answer. And from this, we saw that the confidence interval was 6.5 to 12.5, which gives us that choice. Question number 16. Insurance companies track life expectancy information to assist in determining the cost of life insurance policies. Last year, the average life expectancy of all policyholders was 77 years. We now want to determine if clients now have a longer life expectancy on average. So they randomly sample some of their recently paid policies. They will only change their premium structure if there's evidence that people who buy their policies are living longer than before. So we're looking at two things. Is this a two-tailed test or is it a one-tailed test? Is it about a mean or is it about a proportion? We know that this is about a mean because we're trying to see if the average life expectancy is different. So we can cancel out these two. And is it a one-tailed test or is it a two-tailed test? Are we seeing if they're different or if we're seeing if one is greater than the other? And we're trying to see if people are living longer. So that is what makes it one-tailed. If it said if the average life expectancy has changed, then it would be a two-tailed test. But because we're only seeing if people are living longer, if the mean is greater, that's what makes it one-tailed. Question number 17. A sales manager was interested in determining if there is a relationship between college GPA and sales performance among salespeople hired within the last year. A sample of salespeople was selected, and relevant data is in GPA, and we're trying to see if the assumptions and conditions for regression and inference are satisfied. So we're trying to check equal spread, linearity, nearly normal, and independence. So in order to check these assumptions, I'm going to make a model of units sold, which is our Y, in terms of college GPA, which is our X. So I'm going to make this model. And just like we did, I think in question 2, I'm going to make the residuals of the model using this residuals function. This super convenient function, plot the model. And down here it says hit return to see next plot. So this is going to give you a bunch of different plots. We'll talk about which ones are important. First one, residuals versus the fitted values. And we see this looks pretty good. There's not a clear trend. If it was fanned out like we saw in an earlier question, or if it was curved, there would be an issue. But that looks pretty good. If you look at the normal QQ, this also looks pretty straight. Gets a little weird up here, but overall this QQ plot is just good. Also look at a histogram of the residuals to check the nearly normal question. And it's still putting return to see next plot. So you'll get rid of that. This one we don't care about. Now a histogram of residuals. And this looks pretty normal. It's not skewed in one direction, only one hump. That's good. So all of the conditions are satisfied. Question number 8. On a typical night in New York, about 25,000 people attend a Broadway show, paying an average price of $75 a ticket. So this data file is giving us receipts, paid attendance, percent shows, and average ticket price. Use the regression to model receipts in terms of other variables. So we're modeling receipts, that's our Y variable, in terms of the other variables. The coefficient for paid attendance tells us how much the receipts change if total paid attendance changes. Give a 95% confidence interval for that coefficient. So I'm doing receipts, which is my Y, in terms of paid attendance, shows, and average ticket price. So I just use my LM function with my Y, and then I put a squiggly, and then I put my X's. I put X plus X plus X. So my paid attendance X plus the shows X, the average ticket price X. We can do this all in the LM function. I'm just going to call it model again. You can call it whatever you want. Then I'm going to do summary of model. And this shows that it gave me coefficients, which are the estimates for each. But I don't want the estimate. I want a 95% confidence interval for the coefficient. So how do you do that? There's a function for it in R. Of course there is. It's called CONFINT, the model. This is a super convenient function. It gave me 95% confidence interval. It defaults to it. We're looking for the coefficient of paid attendance. So paid attendance 1 says the lower bound is 0.0747. The upper one is 0.077, which gives. If you did not know this confidence function, you could probably figure it out, or at least eliminate it to a 50-50 shot, because you can look at the summary of the model. The coefficient for paid attendance is 0.007. So when we're looking at that, okay, well this doesn't have 0.07 in the interval. That can't be right. And is 0.07 in the middle of either of these intervals? I don't think so. So that's why you could pick this interval, just if you know this function. Write it down on your cheat sheet so you have it for your exam. Question 19. This is about the same data set that question 18 was about, except it's asking, use regression to model receipts in terms of variables. Based on your results, which variable does not have a statistically significant relationship with the same code I used in question 18? These two lines are the same as these two lines. I'm just going to run it again. And we're saying which coefficient is not statistically significant, which R gives us a And it's this column, this probability. And which one is not less than 0.05 is this one, 0.116. So shows does not have a statistically significant relationship with receipts. Question number 20. A paint supply store wanted to know if the correct amount of paint was contained in 1-gallon cans purchased from a nationally known manufacturer. It is known from the manufacturer's specifications that the standard deviation of the amount of paint is equal to 0.02. A random sample of 50 gallons is selected. The supply store plans to test this, that the mean is 1 versus the mean is not 1, at the 5% significance level. If the average amount of each can is really 0.99, the power of the test is 0.97. If the average amount in the paint cans is 0.99, then the probability of failing to reject the null hypothesis is equal to something. So this is basically a definition question again. Power is the probability of correctly rejecting the null. So the probability of failing to reject the null hypothesis is just 1 minus the power of the test. If you have more questions about this, come see us in office hours or send us an email. This is just a definition question. So it's 0.03. Question 21. Many students entering McCombs as freshmen already earn college credits by passing AP tests or taking dual credit courses in high school. 20% enter with credit for calculus. 12% enter with credit for stats. 3% of freshmen enter with credit for both of those. So let C be the event for calculus. Let S be for stats. Are C and S independent or disjoint? So disjoint means if you're one of them, you can't be the other. So that would mean if you have credit for calc, you can't have credit for stats. But because people have credit for both, some people have credit for both calc and stats, we can eliminate disjoint right away. They are not disjoint. And then we're trying to see if C and S are independent. So independent means the probabilities are the same. So the probability of C times the probability of S is 0.2. The probability times 0.12, which is the stats probability. If we do that, we get 0.024. The actual probability of both is 0.03, just different than 0.024. So that means they are not independent. So that gives us they're not independent, they are not disjoint. Question 22. In the college's dataset, create a regression model that predicts graduation rate from student-faculty ratio and average combined SAT scores. So regression model, think right away, LM function that predicts graduation rate. That's our Y, from student-faculty ratio, that's an X, and average SAT scores, that's another X. Find and interpret the slope coefficients. So we'll LM function with our Y and our squiggly, and then our combined T, which is the first X, plus student-faculty ratio, which is the X. I'm just going to call it model. You can call it what you want. Then a summary of that model. And those are our coefficients. So the slope for the student-faculty ratio, so this is what we're talking about, that's negative 0.734. It's negative, means it goes down. 0.734. Negative 0.734 down 0.734 for each additional student per faculty member. The slope for the average SAT tells us that the graduation rate goes. So that then we're looking at the SAT one. it's positive, so it's going to go up by 0.084 for each 1 point increase in the SAT average. That's just run the LM function, know how to interpret the coefficients. The return of the SPY ETF should theoretically have the following relationship with the return of the S&P 500 index. So SPY return equals S&P return plus some. I want to use the past year of data to test whether the slope is equal to 1. I run a regression of the return of the SPY ETF on the return of the S&P 500 index. The output below shows the regression slope is 0.997 and its standard error is 0.003 something. What is the test statistic for the test saying the null is 1 versus not 1? So this is just knowing how to calculate the t-statistic by hand. So we're testing statistic equals standard mean minus the null mean divided by the standard error. So the sample, when I ran this with my sample, 0.997, and the null mean, I want to make sure they're equal to 1, so 0.997 minus 1, and I divide by the standard error, which it tells me right here, and it also told you down here in the picture, if you wanted to look at the picture. So I run this, and I get that the test statistic is negative 0.845. Number 25. What is extrapolation? So when making predictions using a least squares regression line, y hat equals b0 plus b1x. This is just what we get in LM function. This has been determined from a set of data. Extrapolation occurs if, so we're just trying to figure out what extrapolation is. Do you know the definition of extrapolation? Extrapolation is when we predict a value of y from a given value of x, even though the data has no x values that are nearby. So if you don't understand that, let's just look at a plot. I just made this up so I can explain it to you. So if I had this data set and I made a regression line using this data, so I made a line to go through it, and then I wanted to predict the graduation rate of a college that has a $40,000 tuition. So the data I have only goes $20,000. So it would be extrapolation if I plug in an x of 40,000 and expect to get a good answer. So we only want to plug in data points that are around data that we already have. So extrapolation is if I predict a value of x, y from a given value of x, even though the data has no x values that are around. Question 24. An operations manager was interested in determining if there's a relationship between the amount of training received by production line workers, the age of the worker, and the time it takes for them to troubleshoot a process program. So, trying to see if there's a relationship between training and the time it takes to for them to troubleshoot. So, hours of training and age are time is our y, hours of training and age are our x's. So we took a sample and we got this regression equation. And what this question is basically trying to figure out is, can you interpret what a multiple regression output means? So from this LM equation, A says hours of training and age are excellent predictors of troubleshooting time. This line, this equation, doesn't tell us anything about how good of a prediction it is. That is the R-squared value. So this first one's not right. We don't know that from just the equation. B. So these answer choices are actually a little bit mixed up. So So don't look at this right here because these were for when I took this test earlier, but I will explain these as they are. This is not the right answer. So B, among workers of the same age, each additional hour of training reduces the predicted troubleshooting time by 0.3 minutes. So this part is right because an additional hour of training, which is right here, reduces the predicted troubleshooting time by 0.3 minutes. That's true. What makes this right is this among workers of the same age. Because when we were talking about the interpreting multiple regression output, we have to say among workers of the same age. So given that age stays the same, if I put one more hour of training, then this is the coefficient. So that's why B is right. So this is B. B is right because it includes among workers of the same age. C, the number 2.4 does not have a meaningful interpretation. So this is our y-intercept is C. So that means if I plugged in 0 and 0, I would get 2.4. So a person of 0 age with 0 hours of training, it would take 2.4 minutes for them to troubleshoot. That does not have a meaningful interpretation because that does not exist. So C is not right. C is right. 2.4 does not have a meaningful interpretation because no one has a 0 age and 0 hours of training and can troubleshoot in 2.4 minutes. That's not true. D, a worker that is a year older will spend an additional 0.04 minutes of troubleshooting time. This is not right because it does not include given the same amount of training. In interpreting multiple regression output, if you have to say given that the others are the same. So that's why D is not right, which is this one. This is A. D is wrong because you have to include given the same amount of training. This is just B and C. That's all for this. If you have any other questions, come see us in office hours or for the review sessions, or email any of your TAs. And we will see you next week for your final, and good luck studying for your finals.